SwayamPrabha. Digital India. Educated India.
In today's lecture, we will discuss the flow of ER or MR fluids in the shear mode. Now, all these topics including the constitutive relations of these ER or MR fluids, flow mode, shear mode, all these can be found in sufficient details in the book of Chopra and Sirohi. So, the learners are highly encouraged to read those relevant topics from the book. Now, if we want to talk about the shear mode, then the first thing is that in shear mode the flow is not driven by pressure, unlike what was happening in the flow mode. So, in shear mode also we have two plates at the top and bottom. Now, the top plate is moved by a velocity u0, and that can involve application of a force f0, and the velocity profile across the depth is a result of the movement of the upper plate. It is not due to any pressure difference. So, here we have x, here we have y, and the depth of this region we can call as d. Now, to analyze the flow, again we start with the governing differential equation, which we can write as del tau by del y is equal to del p by del x. In this case I have no pressure difference, so it is 0. So, del tau by del y is equal to 0, that is my governing differential equation. So, the boundary conditions are at y equal to 0, u is 0, and y at y equal to d, and the upper plate u is equal to u0, the velocity at which the upper plate is moving. So, again we solve it under two conditions. One is 0 applied field, now under the 0 applied field my constitutive relation is tau equal to mu multiplied by del u by del y, and then if we put this relation here in the governing differential equation, the expression becomes mu multiplied by del 2 u by del y 2 is equal to 0. So, this equation is solved, and these boundary conditions are satisfied. So, from this governing differential equation we get mu multiplied by del u by del y is equal to C1, and then we have mu into del u by del y is equal to Cy1 plus C2. Then if we say that u at 0 equal to 0, that there is one mistake here. So, if we integrate it once more, we get mu into u equal to C1y plus C2. Then if we put the condition that at x equal y equal to 0, u is 0, that gives me C2 equal to 0, and then if we say that at y equal to d u is equal to u 0, that tells me that mu into u 0 is equal to C 1 into d, and on solving for C 1 we get C 1 equal to mu u 0 by d. So, if we put these two in this expression, we get the velocity profile as u as a function of y is equal to u 0 by d into y. So, the velocity is a linear function of y. It starts from 0 here and it becomes u 0 here. In between them it varies linearly. So, u is equal to u 0, here I have u equal to 0. Now, if the velocity gradient is constant, because the velocity variation is linear, so the velocity gradient is constant, and that tells me that the shear stress is constant. So, we have shear stress tau y equal to mu into del u by del y. From this expression, if I evaluate del u by del y, it is just u 0 by d. So, my tau as a function of y is mu into u 0 by d. So, tau is not a function of y anymore. So, in this case the shear stress variation is constant. So, on this beside the same figure, if I draw the shear stress variation, it is just mu u 0 by d mu u 0 by d, that is shear tau versus y graph for our case. Now that we know the shear stress, we know the velocity, now we can find out the equivalent damping for this case. So, for that what we do is, first let us find out the force F 0. Force F 0 is tau multiplied by L and B. If we look at this diagram, so we have a z axis here. Now, the dimension of these plates along the z axis is B. So, the inner surface of this plate, which is in x z plane, that experiences the shear stress tau, the value of tau at y equal to d. In our case tau is constant. So, it experiences a shear stress of amount mu into u 0 by d. So, the corresponding force, if I multiply that stress by that dimension, by the area of the inner surface of this plate, which is L into B, if we multiply by that, we get the total force F 0. So, F 0 is tau into L into B, which comes to be mu multiplied by u 0 by d into L B. Now, the equivalent damping comes as C equivalent, 0 means when there is no field applied, is equal to F 0 by u 0. So, if I divide F 0 by u 0, finally we get mu L B by d, and which we call mu multiplied by capital gamma. So, capital gamma is a parameter which depends on these dimensions. Next let us do the same thing for a non-zero applied field. So, in this condition we have to write the constitutive relation considering the yield stress. So, tau as a function of y is tau y multiplied by the sine of tau y multiplied by the sign of gamma dot, which can be plus or minus, plus mu into gamma dot, and we know that gamma dot is del u by del y. Now, here if we differentiate this, again we get del tau by del y as just mu into del 2 u by del y 2. So, the governing differential equation remains same, and if the governing differential equations are same, boundary conditions are also same. At y equal to 0, u is 0, at y equal to d, u is 0. So, that gives me the same flow profile. So, from here we can find out u as a function of y as u 0 by d multiplied by y. So, here we can note that governing differential equation and boundary conditions are same as those of non-zero applied field. As those for non-zero applied field. So, we have the same solution. Now, we have to find out the stress. So, the stress as a function of y is just we have tau y multiplied plus mu into u 0 by d. So, only tau y gets added here. So, with this new stress, now we have to find out the equivalent damping for the active case. So, first let us find out the force. Now, the force is F 0, which is tau multiplied by B L. So, finally, the expression comes as tau y plus mu into u 0 by d multiplied by B L. Now, these things can be written in a somewhat different form. We can write tau y multiplied by d by u 0 mu plus 1 multiplied by mu u 0 by d L b. So, with that finally, the expression is, and that we equate with C equivalent for the active case multiplied by u 0. So, on doing that we get C equivalent as tau y d u 0 mu plus 1 multiplied by mu L b by d. Now, this quantity can be expressed as mu multiplied by capital gamma. We know that L b by d is capital gamma, and then this entire quantity is multiplied by 1 plus B I. We can see here that this quantity is again a ratio of yield stress and viscous stress. Tau y is yield stress, mu 0 by d is the velocity gradient, which is gamma dot, and that is multiplied by the viscosity gives me the viscous stress. So, it is tau y d divided by mu 0 u is our Bingham number. So, in other words, we can say that this quantity is equal to C equivalent 0, because we have seen that mu into gamma is C equivalent 0, C equivalent for the inactive case, for the non-zero field case. So, that is C equivalent multiplied by 1 plus the Bingham number. So, here the Bingham number tells me that how much damping we achieve by making the fluid, by applying electric field across the fluid layer. So, more the Bingham number is, more I have the active component of the damping. So, these are the two cases that we have described so far. One is the flow mode, another is the shear mode, and for under each of these modes we have non-zero applied field and zero applied field, and we have seen that in flow mode there are several region that comes out because of the non-zero applied field. In shear mode we do not have that. Shear mode is somewhat more simplified in terms of analysis. So, with that I would like to conclude this lecture here. Thank you.